Hello, in this video I'm going to give a quick demo of this Colab, which is Deep Learning Optimizer tutorial. Let's start with the first coding cell. We start by installing the necessary dependencies like PyTorch, Matplotlib and scikit-learn for our optimization visualizations. There is no visual output here, just a silent installation running in the background. Next, we import all the libraries and functions we'll need, setting up our environment for creating 3D plots and animations. And if we see, the output confirms that PyTorch and all our plotting tools are loaded and ready to go. Next, we generate a single 1D loss landscape to visualize the basic goal of optimizer, finding the lowest point. The output plot shows a curving line with a red starting point and a green star at the global minimum, illustrating the journey our optimizer must take. Next, we step up to 3D and create different types of loss landscapes to show why optimizer is so hard in real neural networks. The output text reminds us that while we visualize in 3D, real models have landscapes with millions of dimensions. Next, we plot the contour maps of these landscapes, including a simple bowl and a steep ravines and a saddle point. The output visual gives us a top-down view of these mathematical shapes, making it easier to see where gradients might get stuck or oscillate. Then we dive deep into saddle points, plotting a 2D contour where the landscape goes up in one direction but down in another. The output explains that saddle points are major challenge because gradient becomes zero, causing simple optimizer to completely stall. Next, if we go to the next cell, here we visualize the actual concept of gradient by plotting tangent alongside a simple parabolic curve. And if we scroll down and see the output, the text emphasizes the core rule of gradient descent. We must say always step in the exact opposite direction of the gradient to go downhill. Next, we build vanilla gradient descent from scratch, implementing the basic algorithm without any bells or whistles. The logs shows the optimizer successfully taking a starting point of 2,2 and stepping it in all the way to loss of 0. Then we visualize the path our vanilla gradient descent took by plotting its trajectory on a contour map. The output graph displays a straight, confident red line marching directly into the center of the simple bold landscape. Next, we experiment with different learning rates from very small to overly large to see how they impact the optimization path. And the resulting grade of plots clearly show that the small rates are painfully slow, while rates that are too large cause the model violently diverge and fail. Next, we shall test our optimizer on a ravine landscape to see how it handles steep slopes mixed with shallow valleys. The output graphs reveal that higher condition numbers causes the optimizer to oscillate wildly back and forth, wasting time instead of moving straight down the valley. Next, we visualize how a saddle point creates a trap for our optimizer using a beautiful 3D surface plot. The output highlights the danger the gradient vanish near the center, bringing leaning to a grinding halt unless we use advanced techniques. Next, we compare batch gradient descent against a stochastic gradient descent on a bumpy multimodal landscape. The plot and text explain that the inherent noise of SGD actually helps the optimizer bounce out of bad local minima and find better global solutions. Next, we implement SGD with momentum, adding a velocity term to help push the optimizer through flat regions. And the output highlights how momentum dampens those wild oscillations we saw earlier, accelerating convergence like a ball rolling down a hill. Next, we implement AdaGrad, an adaptive optimizer that scales the learning rate independently for every single parameter. The output notes that while AdaGrad is smart about steep directions, its learning rate continuously shrinks, which can eventually freeze training entirely. Next, we fix Adagrad's shrinking problem by implementing RMS prop, which use an exponential moving average. The output explains that RMS prop keeps the benefit of adaptive learning rates without letting them vanish over time. Next, we combine the best of both of words by implementing ADAM, which we use both momentums and RMS props adaptive scaling. The output that we see confirms that this powerful combination is exactly why ADAM is the default choice for almost all modern deep learning. Next, we plot different learning rate schedules like step decay and cosine annealing to show how we can adjust the learning rate during training. The graph visually demonstrates these schedules with the text not nothing that warm up plus cosine decay is the gold standard for training large models. Next, we put all the optimizer to test by training a real neural network on a noisy moons dataset. That printed logs show the final loss and accuracy for each optimizer, with Adam and Adam W hitting on impressive 98% accuracy. Then we plot the training loss and accuracy over all curve for all optimizer we just tested. The graph clearly shows Adams and Adam W converging much faster than vanilla SGD through SGD with momentum eventually catches up. Finally, visualize the concept of sharp versus flat minima to explain why optimizers like SAM are useful. The plots show the flat minima are much safer because a slight shift in the weights won't cause a massive spike in the loss, leading to better real world generalization. So that's it with this collab. Thank you.